So first things first, we're going to hop into chapter 16, and we are very briefly going to review some ideas, right? So let's first go through the reactions just to get them out of the way, but I'm going to make a new page. So I'm so sorry for all the scrolling. Please don't do that. Okay. Cool. So we are going to review the reactions. And this is chapter 16 again. So the first reaction we did was the gem diol. And the gem diol was using a ketone or an aldehyde. And what were the reagents for the gem diol reaction? Water, awesome. And what else? There was definitely water, but what goes under the arrow? What do we think? Acid or base catalyst. Awesome. Okay, so H2O. In this one, we're just going to say catalyst because it can be either acid or base. And we end up forming OH, OH. So we get our gem diol. So if we were to do this with, can I duplicate? Maybe, maybe not. Okay, no, I'm just going to redraw it because that was too difficult. So if we were to do this with an aldehyde, what would be the difference in the reaction? What do we think? True, we would have one extra hydrogen here. So I kind of made it a little bit tricky by drawing this nice little normal arrow, but we know that these are both at equilibrium, right? So in the ketone example, is the equilibrium pointing towards the ketone or towards the gem diol? Towards the ketone, exactly. So the long line goes this way, the short line goes this way. How about in the aldehyde example? Do we prefer the aldehyde or the gem diol? Yes, exactly. We prefer the gem diol. So the arrows are just going to be opposite here. Ta-da! Okay. Now, after gem diol, we did something called the acetyl-ketol reaction. And, excuse me, so sorry. Was there really any difference between using a ketone and using a aldehyde? No, there wasn't. Cool. So I'm just going to use a ketone. What were the reagents? An alcohol, exactly. So let's say an R group attached to an OH. And was there a difference between an acid and a base catalyst? Yes, there was. Okay, so let's do acid first. So when we have an acid catalyst, what did we end up forming? The acetal or the ketol, exactly. In this case, we get the ketol. And someone mentioned this earlier. The ketol is basically two OR groups. However, if we have a ketone with, let's say, base or no catalyst, what are we going to form instead? Oh, you guys are already ahead of me. Yes, you form the hemi, exactly. And all that means is instead of having two OR groups, we have one OH and one OR. So I will go ahead and label this. This is the hemi-ketol. And this is the ketol. You guys are doing amazing. So much participation for a Monday morning. Okay, so I'll leave this up for a second or two. The next reaction that we did, I believe, was the imine reaction. So, also, I know I'm super zoomed in. I promise once we get to the end of the page, I'll zoom out. But yes. All right, so when we are doing the imine reaction, we can start with a ketone or an aldehyde. Oh, my screen is frozen. I hope it has not been like that for a long time. Is that just me, or is the screen really messed up to you guys? Okay, someone said no, it hasn't been like that for a long time, but it is kind of messed up. So here, I'm just going to real quick try and fix that. Okay. Yay, we're good. Okay, someone asked a question about the acetal-ketol reaction, so let's go back to that right quick. So someone said, how do we know how many carbons are attached to the R group? So you are going to base that entirely on what the alcohol is. So let's say you have OH. You're going to make an acetal or ketol that has O. 1, 2, 3. 1, 2, 3. O, 1, 2, 3. Yep, you're very welcome. Okay, so then the imine reaction, we're going, I don't remember if I asked you this or not, so I'm just going to go ahead and write it. The imine reaction uses a primary amine, which has one R group and one NH2. And the R group here is going to be exactly the same as the acetal-ketol reaction. So whatever they give you, that's the one you attach. And what do we form when we react a primary amine with a ketone or an aldehyde? The imine, yes, it's right in the name. I'd love to see it. Okay, cool. So the imine is essentially where you take the bottom half, you keep it exactly the same, and then you take this guy and you replace the O. We go bam, 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 bam. Are we bringing any of the H's over? No, because we have too many bonds. Exactly. Cool. Stellar. All right, the next one that we're going to do is the enamine reaction. And the enamine is similar to the imine, but what is the difference in reagents? Actually, before you tell me, I forgot to write any catalyst is good here, so I'm just going to write cat. And yes, you guys are totally right. We need a secondary amine. So I'm going to scroll a little bit. We have secondary amine, which looks like so. And again, we're going to have any type of catalyst. So this time, instead of making an imine, we're going to make an enamine, correct. And I'm actually going to change the ketone slightly here. I'm just going to give you this. And the reason I do that is to remind everyone. Oh my goodness, if I could draw, that would be cool. All right, so we know that the enamine is different than the imine because instead of having a double bond to the nitrogen, we have a single bond. And then the nitrogen is attached to its two R groups. And we have a double bond, but it's in a different spot. So the double bond will be between the alpha carbon and the carbonyl carbon. And in this case, we have two alpha carbons. Which alpha is going to make the double bond? Sorry, I felt a hiccup coming. Alpha 1, exactly. And that is because that position is more substituted, so we get a better double bond. Stellar. Cool. So let's zoom out a tad. And let me actually move this over because it's killing me. There we go. Cool. So after the enamine reaction, we did the hydrozones. So first we have the hydrozone. And the hydrozone reaction is between an aldehyde or ketone and what reagents? Hydrazine, exactly. And a hydrazine is basically an NH2 attached to an NH2. And it can have any catalyst. And so we end up knocking off the top part, which is the oxygen, and leaving the ketone part. Sorry, that's a really weird way to say that. We knock off this part, we keep the bottom part, right? And all we do is replace the oxygen with one of the nitrogens, which is attached to another NH2. So are we keeping any of the hydrogens on this carbon? Any of the hydrogens on this nitrogen? Words have no meaning. It's too early in the morning. Correct. We are not bringing any hydrogens over because that nitrogen is fully substituted. Cool. So after the hydrozone, we have a reaction that's almost exactly the same, and it is called the phenylhydrazone. And the phenylhydrazone is only different in that we have a lovely phenyl group attached to our hydrazine. Once we attach a phenyl to our hydrazine, what's the new name? Phenylhydrazine, exactly. Bam, bam. And we're going to use any catalysts, all right, cat. And we're going to keep the bottom part once again. And now, which nitrogen, 1 or 2, are we going to attach to the double bond here? 1, absolutely, and that's because of steric hindrance. So nitrogen 2, is never going to attach to the carbonyl carbon because there's too much steric hindrance and too many bonds present. So we have N attached to an NH attached to a pH. So I think this is a good time to zoom out, and I'll go back to the top so you can see these ones. And now I'm going to go down so you can see these ones. And now we have our oxime reaction, which I will go ahead and draw. It's in the same category in my brain as the hydrozone reaction, but if you don't see it, that's okay. You can treat it as its own thing. Again, we have a ketone or an aldehyde. We have any catalyst. And what are we going to use as our reagent? The hydroxylamine, yes. Or hydroxylamine, however you want to pronounce it, is A-okay with me. All right. So, what's going to act like the nucleophile? Is it going to be the OH or is it going to be the NH2? The nitrogen, exactly. And the reason the nitrogen is going to act like the nucleophile is because it is less electronegative, which means it's more likely to share its electrons. So we're going to keep the bottom half of our ketone and we replace the oxygen with our nitrogen, which is attached to an OH. Ta-da! So here, let me zoom out for you. And that is pretty much chapter 16 in a nutshell. There's also the Wittig reaction, but I have a whole bunch of practice problems for the Wittig reaction. Maybe not a whole bunch, like 3 or 4. But yeah, I don't want to spend time on it now. We'll go over it with the practice problems. Any questions on chapter 16 at all? I'm going to have some of my coffee, and I'll give you a moment. We went through that in like 20 minutes. It's pretty good. Okay, if there are no questions, I will go ahead. Okay, cool. Some conceptual things he can ask for chapter 16. I have some examples, and I don't want to ruin it, like give you guys the answers right now before we do it. So we will cover that in like 20 minutes. And if it doesn't answer your question, please ask me again. Okay, cool. So chapter 17. All right. So chapter 17 deals with nucleophilic acyl substitutions. And I'm going to tell you a little secret. Chapter 16 is almost exactly the same as chapter 17. And a lot of times people will get super like overwhelmed and they kind of will like be like, oh my God, they're all new reactions and they all look similar and I don't know what to do. I promise it's not too terrible. You just gotta like kind of keep it together and think about connecting the dots instead of trying to just memorize things. Excuse me, memorize things. And I know that's easier said than done, so let's go through it. First of all, we're going to talk about reactivity, and Dr. West gave like a nice little table. He gave a couple different like tables and figures in his PowerPoint, and they're kind of hard to understand sometimes if you don't know what you're looking at. So we're going to also like kind of simplify, but I definitely recommend looking at his figures. They're really cool. So we did a similar kind of question where we ranked the order of reactivity, but we did this with just like ketones, aldehydes, carboxylic acids, things like that. So now we're using a group of molecules called carboxylic acid derivatives. Oh my goodness. So carboxylic acid derivatives are basically anything that has a carbonyl with a leaving group on it. And And we are going to, let's go ahead and name these first. So what's this guy? Carboxylic acid. Cool, cool, cool. So we're going to call that, oh my goodness. And next up, ester. Cool, next up. Amide, exactly. All right. These are the new ones. Any idea what this lovely thing is called? An acid halide, cool. And once you substitute the X for a halogen, you can call it an acid bromide, an acid chloride, anything like that. You can also call it an acyl halide. That's also fine. They're interchangeable. All right. So S within our group, what do you think we call that? A thioester. Cool. And last but not least, this guy. It's not an ether, but I see where you're coming from. It's like a double ester almost. And if you don't know what that's called, that's completely fine because you can't really like derive it from your brain. We're going to call it an acid anhydride. An acid anhydride. So let me zoom out so you can see all of those. And I'm going to say this is A, B, C, D, E, and F. And we're going to go about organizing them from most reactive to least reactive. So the absolute most reactive of these guys is D. Acid halides are super reactive. And it just got dark in here. Cool. So acid halides are super duper reactive. After acid halides, we have our lovely acid anhydrides. After our acid anhydrides, we are going to use, okay, fine. Let's think. I don't want to confuse you guys, so I'll give you like the explanation now rather than just give you the answer and then explain. So acid halides are super reactive because the halogens really want to leave and they want to go react and be something else. They're super reactive. Then once you're down to oxygen, nitrogen, and sulfur, you do kind of have to think about electronegativity and stuff, as someone mentioned in the chat. So between oxygen, nitrogen, and sulfur, the one that is most likely to act as a leaving group is going to be oxygen, because again, it's the most electronegative of the three, so it wants to keep its electrons to itself. It does not want to share. So between a carboxylic acid, an ester, and an acid anhydride, you have to figure out which one is the best leaving group. And the best leaving group of the three is actually going to be the anhydride, this one. And that's because when it leaves, this whole thing is going with it, right? There's all that resonance stabilization, super electron withdrawing. It's going to be a really great leaving group compared to these two tiny little things. And then after the acid anhydride, we're going to have carboxylic acid and ester, because those are the other two oxygen-based ones. And they're actually going to be approximately the same. So I'm going to say A and B are approximately the same. And I say that because they're not exactly the same, but for the purposes of this class, you can pretty much say they're the same. After those two comes the thioester, because sulfur is the next best leaving group. And last is going to be C, because the nitrogen is least electronegative. We talked about how good of a base it is. It's really good at giving its electrons away. It wants to make that bond, so it's happy and comfortable. It's nice and stable. It's not super reactive. It's not super eager to break apart and be a leaving group. So I will give you 1 second to think about that while I turn the lights back on. Okay, cool. So any questions about the order of reactivity? Yeah, exactly. So you think of them in the context of leaving groups, and then think about their electronegativities. Okay, so the next thing here is kind of like a fill-in-the-blank thing, and it says nucleophilic acyl substitutions typically go from blank to blank. And so they're typically going to go from more reactive to less reactive. And this kind of makes sense, right? Because in the world, we don't want things to be super, super reactive. We want them to be stable. And the reason reactions happen, usually, is to get things to become more stable. So in these kind of reactions, we always want to go from something closer to the more reactive side to something closer to the less reactive side. And I'll just mention here, more reactive, less reactive. I'm so sorry, excuse me. Okay, so does this reactivity stuff kind of make sense? Okay. So let's go into naming, which I'm sure is your favorite thing in the whole wide world, right? You miss IUPAC, right? No. So the way we name esters tends to confuse people, but I promise it's not that bad once you get a hang of it. So first things first, let's define the suffix. And so the suffix for esters is O8. That is pretty much, just know that, The next part is what's kind of tricky. And so we are going to break it into pieces, right? We know that this part is the ester group, and we know that that is going to be the suffix because it's the highest priority functional group, the biggest deal. So we're going to, at the end, put O8. And then from there, we have to define this group and this group. And I know these colors mixing together are kind of ugly, but the purple blue side is going to be the first one that we name, and the side coming off of the carbonyl is going to be at the end. And we can think of it as this is the main parent group, right? And this chain is coming directly off of that carbonyl. So we can say it's going to be attached as one piece. And we see 2 carbons here, and I will number that for you. 1, 2, 1, 2, 3. And so we're going to say that here we have a propyl, and here we have a ethyl. I'm sorry the colors don't match up. This good note thing is very new to me. So we're going to go ahead and name this propyl. The side with the oxygen always comes first. So we have propyl. And then we have the side coming off the carbonyl. So we're going to say it's propyl F. And instead of saying ethyl, we're going to say ethanoate. So altogether, this guy is propyl ethanoate. I'm just going to move this a tad so we don't run out of space. Alrighty, so let's do that one more time. We have our purple group. How many carbons are on the purple group? So yeah, we're pretty much going to treat the R group here kind of like a substituent. That's a good way to think about it. Okay, so here, yes, we have an ethyl. And here we have a propyl. And obviously we have this lovely thing in the middle. And so we're going to call this guy ethyl propan OH. I think I have one more example. Yes. Okay, so this guy is actually special, and I put him there because Dr. S will sometimes try to trick you on this stuff. So what is the common name for this substituent? Yes, but I mean specifically like this organization of carbons. Isopropyl, exactly. So we're going to call this isopropyl. We're going to call the other side simple. 1, 2, 3, 4 carbons is a butyl. And we know in the middle is our ester. And so we're going to call this lovely fella an isopropyl butan OH. This is the common name. However, the official IUPAC name would not use isopropyl. It would actually use 1, 2, 1 methyl ethane. So 1 methyl ethane would be the IUPAC name for that substituent. So the IUPAC name for this molecule would be 1 methyl 1 methyl ethyl, and we keep the butanoate. Butan OH. And I'll just write here, IUPAC. That was an ugly arrow. Common. So I'm going to zoom out so you can see all of these together. Any questions about naming? I'll give you a moment to write it down or take a picture or whatever you would like. All right. If not, we're going to start the reactions for chapter 17. Yay. I tried to scroll on my laptop. That's not how you do it. Okay, so I did include the answers to this handout in the cheat sheet thing because I just felt bad. There was a lot going on. We didn't really cover this in SI before today. But I know this chapter can be super confusing if you just look at the notes and don't have any explanation. So I'm going to redo it even though you guys have the answers to it. That was a really long explanation for no reason. That's okay. So the general reaction mechanism for this whole chapter is going to be exactly the same. And it's going to go something like this. So we know our nucleophile has these electrons, right? I'm so sorry. I have the hiccups today. So the nucleophile is going to attack the carbonyl carbon, bring those electrons up. We've seen this before, haven't we? Now, electrons go up. We have our nucleophile attached, and we still have our leaving group. So now these electrons come back down, and they kick off the leaving group. So we end up reforming our double bond, and now the nucleophile has taken the place of the leaving group. Ta-da! Any questions about the general mechanism? Okay, if not, I'm going to do one long reaction mechanism where I do all the steps, and then from now on we're going to do it the shortcut way, which I personally love. Let me actually make a brand new page. All right, so the example we are going to use is carboxylic acid. And we are going to use an H2 and let's say HCl. Okay. So this set of reagents should look really familiar. If we were in chapter 16, what reaction would be happening? The imine reaction, absolutely. But the way we can distinguish this from the imine reaction is the imine reaction only happens with an aldehyde or a ketone. This is a carboxylic acid derivative. So instead, we're going to do a substitution. All right. With an acid catalyst, what is always the first step? Protonate, exactly. So we're going to steal a hydrogen, and we get a plus charge. And that makes the electrophile more electrophilic, and it makes it easier for the nucleophile to attack. So please remind me, what atom specifically acts as the nucleophile? The nitrogen, exactly. So the nitrogen, boom, bow, attacks, bring these electrons up. And we get, boom, and boom, and Alrighty, so this is almost familiar to us, right? Now, we told you, or I told you, that the leaving group is going to come off and we're going to reform this double bond. So we can use a handy dandy tool from last chapter called an intramolecular proton transfer. I'll just write that down. And we're going to use the lone pair on the oxygen of the leaving group, and it's going to steal a pair, it's going to use a pair of its electrons to steal a hydrogen. And what's the purpose of doing that? Someone please enlighten me. Come on. What do you think is the purpose of giving a nitrogen to the OH? It takes the plus charge from the nitrogen and gives it to the oxygen, exactly. And so now that the oxygen has a plus charge, it's a better leaving group. And so we're going to use these electrons from the oxygen, not from the nitrogen. And we're going to bam and bam. And now we get this bad boy. If we have a plus charge and we have a hydrogen present, what is the best way to get rid of that plus charge? And while you answer that, yes, this recording will be available today. I am hoping to upload it like as soon as it's done. It just depends on how long it'll take to process. Deprotonate, yes, and we're going to use Cl-, which is floating around in our solution, and we snatch it, pow. And yes, indeed, we will have SI today at 3 as well. That session is not being affected by this extra session at all. Bam. So let me zoom out for you. So we went from a carboxylic acid to an amide. Did we go from more to less reactive? Yes, we did. Yay! So we did go from more reactive to less reactive. Awesome. So now that you've seen this whole thing, I'm sure every single person in the room, or in the chat, is wondering, Rosemary, how do you do it the Rosemary method? I got you. All right, so we're going to take all that complicated stuff, and we're not going to throw it in the garbage, because that would be irresponsible of me to say, but we're going to just put it in a little box and hide it under our beds. So, I forgot already what I gave you. Okay, cool. All right, Rosemary method time, right? We see primary amine, we see acid catalyst, and we see carboxylic acid. So we automatically know this is no longer a chapter. Oh my goodness. That was entirely overwhelming. I'm so sorry. We are no longer doing a chapter 16 question. We're doing a chapter 17 question. So first step, define the leaving group. Second step, define the nucleophile. And now all we do is redraw this part of it because that's not going to change. And we replace the OH with the nucleophile and whatever group is attached to it. And we're going to get rid of one hydrogen because we know nitrogen can only have 3 bonds. 1, 2, 3. So here we have the full version. Here we have the Rosemary version. How are you feeling with this reaction? Let's say 1 out of 5. 5 is pshaw. This is so easy. And 1 is I have no idea where I am. 4 with the shortcut. Hell yeah, dude. Yay. Okay. Coolio, 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 coolio. And, give me a moment to plot. Okay, there's like 5 pages of like examples for you guys to do, so I highly recommend you go through and do them. We're not going to go through all of them right now. We will go through some of them in SI today. I am going to stop sharing my screen for one moment though, because I just want to double check. We covered that, we covered that. We covered that. We covered that. Okay. I'm just looking at Dr. West's list of chapter 17 stuff to cover because I don't want to give you anything you don't necessarily need for this exam. So let's reshare. All right. So we're going back to the first page and I'm going to answer this question. What reagent would need to be used to make an acid halide from a carboxylic acid? So essentially, there's a couple things I want you to take away from this. You are forming this guy. And we said that we want to become more stable or less reactive. And we know that this guy right here is super duper, so super that I can't even spell, unstable, aka reactive. And so you can't just do a normal chapter 17 substitution reaction and expect to get a acid halide because that's ugly. We don't like it, right? Instead, we have to use some other reagent to get from this to this. And just to make it a little bit easier, let's, instead of giving this just X, let's give it BR. Give it a name, become more personal. So we have to find a set of reagents that can turn OH into a BR. Do we happen to know such a reagent? Well, we're turning it into a halogen. So what reagent have we seen this semester that turns OH into a halogen? Someone got it. Yay. Okay, PBr3. Exactly. So everyone forgets about that by this point in the semester. So I'm so happy you remembered. So PBr3 PBr3 is going to turn an OH into a Br. So let me actually zoom out because that was kind of aggressive of me. So yes, does anyone remember any of the other reagents that had a similar... Yes, okay, so there's also PCl3, PCl5, SOCl2, things like that. Someone said like FeX3. So that one is actually from chapter 15. I'm glad you thought of it because it does seem really similar, but that's just going to act as a Lewis acid. It's not necessarily going to undergo this reaction. So it's really important that you kind of categorize things in your brain because, again, they do seem super similar. So this group is going to act as protecting groups and turning OH into halogens. And then FeBr3 is going to be a catalyst for chapter 15, if that makes sense. So here, let's zoom out. So the only way, it got dark again. The only way to form an acid halide is to use a carboxylic acid and one of these reagents. Let's see if it'll turn back on. I'm in here, I promise. No, it doesn't like me. That's fine. All right, so any questions on chapter 17 so far? I promise I'm in here. Okay, thank you. All right, if not, let's go here. We are not going to cover lactones and lactams because that wasn't on the list of stuff, as far as I know, that you have to know for this exam. So we're gonna put a pin in that until next time. We are, however, going to go over here and we are going to do these a couple, excuse me, I can't speak today. We are going to do a couple of these examples with the Rosemary method. So, step number 1, we see leaving group, we see nucleophile, and we get rid of a hydrogen. So we get this attached to O, attached to the R group. Questions, comments, concerns? If not, let us go to the next one. So this one is what always trips people up. The anhydride. So the anhydride is going to have this whole thing as a leaving group. So remember, oxygen-carbon bonds are the ones that are going to break. So we're going to break this bond here. And that whole yellow part will act like a leaving group. Next up, we define the nucleophile, and we know it's nitrogen. And then we get rid of one of the hydrogens. So I'm just going to cross out the number 2. And we get this. Bam. Bam, bam, chicka-bam. Are we feeling semi-comfy with this one? Yes, okay, super sweet. So let's do a couple on this page as well. I'm gonna do the harder ones with you and you can do the easier ones by yourself. The shortcut makes it a lot easier. Yay, I'm so glad to hear. Okay, cool. So in this example, leaving group, bam, nucleophile, bam, and we get rid of a hydrogen. So we end up keeping this original base exactly the same. And the only thing we're changing is bam, bam. So we went from a carboxylic acid to an ester. Here we see anhydride, so this whole thing is our leaving group. This is our nucleophile. And we get rid of a hydrogen. So we end up with pew, 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 pew. Ta-da! Okay, any questions on these two? If not, let's perfect. Let's do this one. Alrighty, so this is kind of, I want to say next level difficult, but you guys are rock stars, so it's going to be easy peasy for you. And if it's not, that's okay, we'll go over it. So, things are in a ring. Usually people see rings and they're like, okay, everything is different now, I'm gonna die. But I promise, it's not different and you're not gonna die. So, first of all, what is this functional group? Do. What's the functional group? Do. Functional group. Anhydride, yes. So it's just a cyclic anhydride. Cool. And so we are geniuses, right? And so we remember that when we have an anhydride, it's going to break here or on the other side, doesn't matter. And this whole thing acts like a leaving group. And we know that a leaving group, if it's on a ring, is not going to completely just go away. It's going to open up. So never forget to count your carbons. I'm going to start here. 1, 2, 3, 4, 5. You could have theoretically started anywhere, but I like going this way. Next step, we see S. We know S is our nucleophile. We know we have to get rid of an H. So let's draw out this structure. I am going to put carbon number 1 here and go 1, 2, 3, 4, 5. And on carbon 1, we attach the nucleophile. So we attach S. On carbon 5, what are we going to attach here? What do we think? Not nothing, because we can't have a plus sign. We're going to have the O, exactly. So we can't forget about this guy. It doesn't just disappear. So we get O. And we don't want O minus, so we're going to add an OH. So in summary, if we have a ring like this, an anhydride, one of the sides is just going to turn into a carboxylic acid, and the other side is where you will attach your nucleophile. Any questions on this one? I know it's a little bit more complicated than the ones we have done. If no question, we will do this last one and then move on to practice problems. Yay. Okay. So this one is a little bit different and it doesn't have a reagent here, right? This is super weird. It only has this thing, NaH. And so NaH can be broken down into Na plus, H minus. So anything with a negative charge can be a what or a what? A nucleophile or a base, exactly. So in this example, it could either be a base and steal this hydrogen, or it could be a nucleophile and attack. What do you think is easier for that nitrogen? To do a whole reduction reaction or to steal a hydrogen? What do we think? One or two? One. I would definitely have to agree with you. So in this reaction, since it's easier to be a base than a nucleophile, that's what N minus is going to do. So it's going to take its electrons, steal a hydrogen, and give those electrons back to the oxygen. So we get O minus. Gasp. We have an O minus. Anything with a negative charge will be a what or a what? A nucleophile or a base. Thank you very much. So it's actually going to act like a nucleophile this time, and it's going to attack itself. And so this ends up being exactly the same reaction as all the other ones from chapter 17, but now you're making a ring. And as Miss Rosemary, I hated that, as Rosemary always says, we're going to count our carbons. So I'm going to count 1, 2, 3, 4, and the oxygen is going to be in the ring this time, right? Because it's directly attacking the carbonyl carbon. So I'm going to count it. All right, so we're making a 5-membered ring. I always like to put the oxygen in that corner. It's really up to you. So we get 1, 2, 3, 4, 5. On carbon 1, we have O minus, and we have Cl. Oh, darn it. Cl. And on carbon 4, we have a methyl. So all we're going to do is bring down those electrons, kick off the leaving group, and we get this handsome molecule. Oopsie. So we kind of stepped up the difficulty and we did an example where we break a ring and an example where we make a ring. How do we feel about these rings? 0 to 5. I can't tell if it's thunder that I hear or if there's just cars driving, but I hope you guys don't hear it. Come on, friends. How do we feel? Are we okay to move on? I don't want to move on if anyone's super confused. Yes, I can definitely explain to what happened. All right, so someone asked, what happened to the double bond right here on carbon 1? So when we attacked, that was completely my bad. I didn't draw this arrow. So when we attack here, these extra electrons from the extra bond move up here. And that's why we have a single bond and we have a negative charge. Okay, you're very welcome. Alrighty, so the rest of these I recommend you do on your own for practice. We're going to do a couple more of them in SI today. And we're about ready to move on. So I'm going to end the recording. And then the next video will be just full of practice problems. So I'm going to stop the recording now.